Okay, I want to give you a few more definitions and help you to understand a couple different ways of seeing or analyzing hydrogens and carbons within organic molecules. These are the types of questions you could expect to see on an exam or in your homework. And let's talk about what they're asking. This first one says, how many of each type of carbon are in this molecule right here? And then it's this funny one with a little circle. This I would pronounce or call this primary. This is saying primary, secondary, tertiary, and quaternary. Let's go to our course notes. Okay, you see in the nomenclature of the course notes, we have primary, secondary, tertiary, and quaternary to describe these carbons with the arrows pointing at them in these different environments within molecules. So a primary carbon is basically a carbon in a molecule that is attached to only one other carbon and otherwise has hydrogens attached to it. And it's all single bonds too. If we started to bring double bonds or triple bonds in, that would no longer be primary. So it is a regular old carbon that has 4 bonds to it, 3 of which are to hydrogens and 1 of which is to a carbon. And I don't have this in the notes, but if you are a hydrogen that is bonded to a primary carbon, then you yourself are a primary hydrogen. You would be called a primary hydrogen. Basically, that's how the trend goes. If you are a secondary carbon, you're attached to 2 other carbons, and then the rest of your bonds, 2 more, go to hydrogens. If you are a secondary hydrogen, then that means you are bonded to a secondary carbon. Tertiary carbons have single bonds to 3 carbons, and then its 4th bond is to that one tertiary hydrogen that's hanging out on it. And then lastly, a quaternary carbon has 4 single bonds only to other carbons, and there are no quaternary hydrogens because you can't fit a hydrogen in when the carbon is already bonding to 4 other carbons. Okay, knowing what I just showed you in the course notes, why don't you pause this video, and you could probably even work on both of these problems right here. We haven't yet talked about carbon and hydrogen environments, so don't worry about that, but go ahead and fill in how many primary, secondary, tertiary, quaternary, etc. we have in each of these molecules. Okay, and you worked on it, now you're back. Let's see, how many primary carbons do we have in this molecule? That would be a carbon, like this one right here, that has 3 hydrogens on it and is bonded only to 1 other carbon. So we have 1 primary carbon right here, and we have 1 primary carbon right here. Those are the only 2 methyls we have in this molecule. So there are 2 of them. And then in terms of hydrogens, that would be only the hydrogens that are hanging out on the primary carbons. So there's 3 here and 3 here. We have a total of 6 of those hydrogens. And now we're looking for secondary carbons. They must be attached to 2 other carbons. If I look at this one right here, this carbon in this molecule, it's actually attached to 1, 2, 3 carbons. So that would not be secondary. We'll come back to it. Here's a carbon that has 1, 2 bonds to 2 other carbons. So that would be a secondary carbon. And this one down here would also be a secondary carbon, 1, 2 bonds to carbons. On the other side of the ring, very similar looking situation. I think we have a total of 4 secondary carbons in this molecule. How about hydrogens that are on those secondary carbons? Well, there's 2 here, 2 here, 2 here, 2 here. We have a total of 8 secondary hydrogens in this molecule. And tertiary, okay, now that's the carbon here that's attached to 3 other carbons. This one is tertiary, and so is this one down here. There's a lot of symmetry in this molecule that we're looking at. So I think we ran out of carbons. There's the last 2 remaining carbons in this molecule are tertiary, and they each can only have 1 hydrogen attached to it. They already have 3 bonds to carbon, only 1 H here, 1 H here. So there's a total of 2 tertiary hydrogens. I don't see any quaternary carbons in this molecule, none that have 4 bonds to other carbons, so that would be 0. There's our first question. Now we'll come down to look at this one. Okay, I see a lot of primary carbons in this one. Here we have one. Here we have one. Anytime you have a methyl hanging off somewhere, that's going to be a primary carbon. So we have 1, 2, 3, 4, 5, 6 primary carbons. And then if we count the hydrogens, 3, 6, 9, 12, 15, 18. 18 primary hydrogens. Let's see, secondary carbons. Well, let's see, not this one for sure, right? This one looks secondary. It's attached to 2 other carbons. This one looks secondary, 2 other carbons. This one is secondary, and not that one. So 1, 2, 3. 3 secondary carbons. And in terms of hydrogens, there would be 2, 4, 6 of those. Tertiary, I don't see any tertiary carbons in this molecule. There are no carbons that are attached to 3 other carbons, which means there are no tertiary hydrogens. If we don't have tertiary carbons, we can't have tertiary hydrogens. And now lastly, here we finally get to see some quaternary carbons. There's one right there, there's one right there, there's 2 of those, and of course they do not have hydrogens on them. So nice job if you're able to identify all of those. Now we're going to think again about these 2 molecules, and we have a different question. This is to prepare you for learning about some spectroscopy, some approaches to analyzing molecules in the lab. Like if you're working in the lab, you're mixing chemicals and stuff, and you say, oh, I made a whole new compound that no one's ever made. You need to prove that you actually made it. You need to somehow prove what the molecule looks like. And so there are a lot of different instruments or machines that you can put your solution or your compound inside of, and they can analyze it and tell you information about its structure. And NMR, nuclear magnetic resonance, is one of those techniques. In the future, you're going to be learning how to interpret NMR spectra and analyze information that comes from an NMR. So this is the very first baby step of being able to understand that NMR information. What you need to be able to do is look at organic molecules and figure out kind of 2 related things. This question is saying, how many unique carbon environments are there in this molecule? Another way to say that is, if you look at this molecule, how many of the carbons are equivalent to each other? So there is actually, let's see, 8 carbons in this molecule. 1, 2, 3, 4, 5, 6, 7, 8. And it could be that there are 8 unique carbons or 8 unique carbon environments in this molecule where all of these carbons are different from one another. But remember how I said there's lots of symmetry in this molecule? We could draw a line through this molecule this way, and if we folded it in half like this, if we folded the bottom up on top of the top, everything would line up perfectly. And what that tells us is this carbon right here is really identical to this carbon right here. Everything about them is the same. They are in the exact same situation as one another. And you know what? I could even draw a line like this too, where I could take the right half and fold it over onto the left half, and everything would line up perfectly, which tells me that this carbon right here is in the exact same situation, identical to this carbon over here. So I don't think the answer to this is going to be 8, that we have 8 unique carbon environments, because I think there are many carbons in this molecule that are equivalent to one another. And maybe that helped you a little bit with trying to figure out how to answer this question right here. If you want, go ahead and pause me and work on it. Otherwise, I'm going to go into answering it right now. Okay, so for sure we said, I think I'm going to use letters now. We said that this methyl and this methyl here are equivalent to each other. And there aren't any other methyls in the molecule. So I am going to call those carbon A. That is one environment for carbons in this molecule. You could be in that environment where you're a methyl sticking off the ring. Now let's see. Oh, these tertiary carbons. There are no other tertiary carbons in this molecule. And if we fold it, they're going to overlap on top of each other perfectly. So they are equivalent to each other, but not to any other carbons in this molecule. So we'll call that environment B. So far we have 2 unique environments. And now let's see. This CH2 right here if we fold the top down, overlaps perfectly on this CH2 right here. So they are the same as each other. And then also if we fold the right over the left, these both overlap over these two. So that means all four of these secondary carbons right here are in the exact same situation as one another. Let's see, so I'm going to call them all C. This is environment C. And there's a total of 3 unique carbon environments in this molecule that we found. And in terms of hydrogens, I think it's the same thing. All of these carbons that we've identified also are connected to hydrogens. And so the C hydrogens are all the same as each other. The 2B hydrogens are the same as each other. The A hydrogens. So there are also 3 unique hydrogen environments. Another way to think about it is if I looked at like this carbon right here and I told its story to somebody, I said, well, it's connected to a CH2 on one side and a CH2 on the other side. And if I continue through the molecule as I go up, I come to a CH3 that's coming off of its neighboring CH2, plus I continue around the ring. And then I come down to this carbon. I say, well, it has a CH2 on each side, and if I keep going this way, then now I come down to CH3. If I told the story of this carbon's situation, this one right here in this molecule, that story would be identical to this carbon's story, this carbon's story, this carbon's story. That's another way to double check. Okay, and now it's your turn to apply this same concept of figuring out the number of carbon and hydrogen environments to this molecule right here. So if you haven't done so already, pause the video, analyze this molecule to figure out how many unique carbon environments there are and how many unique hydrogen environments there are. Alright, and you're back. So let's start to look at this molecule. Well, there is some symmetry in this molecule, right? If we drew a line right here down the middle like this. Sorry, that's not very straight, but I think you get the idea. And we folded the right half over onto the left half, there would be a lot of overlap that we would see here. So why don't we start by looking at this left side over here. We have a methyl on the end, and if we did that fold I was just talking about, this methyl would go right on top of that one. So those are equivalent carbons and hydrogens. They are in the exact same environment as one another. And if we tried to tell their story to someone, we would say, okay, this one is an end carbon of a 1, 2, 3, 4, 5, 6, 7 carbon chain. And when you go to the carbon adjacent to it, it has 2 other methyls attached to it, and then we see a CH2, and then a CH2, and another CH2, and then we come to a quaternary carbon, right? A carbon that has 4 carbons attached to it. 3 of them are methyls. And if we said the story for this carbon, it would be the exact same story. It's an end carbon of a chain of 7 carbons. Its neighbor has 2 methyls, then you go further, CH2, 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 and finally you run into a quaternary carbon that has 3 methyls attached to it. So they are identical carbons. Now, up here we see some other primary methyl carbons, and just because they're all primary carbons does not necessarily mean that they are equivalent to one another. So you can't just make the assumption that all primaries are equivalent, all secondaries are equivalent, etc. However, if we look at these methyls situations, they are actually attached to the same carbon that this methyl is attached to. All 3 of these methyls are attached to the same carbon. And this bond right here has free rotation around it. So if we spun this bond around, these methyls would basically take turns all being in the exact same position as one another. And that does make them equivalent to one another. So this methyl here is the same as this methyl, so is this methyl. And on the opposite side, these 2 methyls, which would fold over right into place with these methyls over here on the left side, are also equivalent. So I'm going to circle these because there's so many of them around the molecule. It looks like we have 1, 2, 3, 4, 5, 6 carbons that are all in the same A environment as one another. So that's one unique environment that has 6 equivalent carbons and 3, 6, 9, 12, 15, 18 equivalent hydrogens. All right, let's work our way down the molecule. We started on the left side. Now, oh, here's a carbon right here, right? The carbon that all 3 of these methyls are attached to, this quaternary carbon, that is unique. It's not the same as any of these methyls right here. So now we see a new carbon environment, and we don't see a new hydrogen environment because there are no hydrogens attached to that carbon. Are there any other carbons in this molecule that are equivalent to this carbon I've labeled B here? Yes, there's this one over here, right? If we fold it on this red line, it would overlap exactly with this carbon right here. So they are equivalent to each other. And we'll keep going. Now we see a CH2, and we haven't seen any other secondary carbons, no other CH2s. So that's going to be a new environment that we see right there. And this is also a CH2. This is also a CH2. This CH2 right here, which if we folded it over would go right on top of that one, is exactly the same. These are in the same environment that I'll label C. And if we told their story, basically the story would be exactly the same for these two CH2s. Check it and see if you don't believe me. However, this CH2 up here that I already have labeled D is different from either of these two CH2s. If you told its story, right off it's different. It's a CH2 that on either side of it has CH2s attached, and there's no other carbon like that in the molecule. So it is unique. And if we add up all of these carbon environments, A, B, C, D, there are 4 unique carbon environments in this molecule. So the answer here is 4. And if we think about hydrogen environments, each one of these different carbon environments has hydrogens on it except for B. So I think we're just going to have one less hydrogen environment than we have for the carbon environments. We have 3 different hydrogen environments. And so this is a question that you should be able to answer if someone asks you, or if a test asks you how many carbon environments, how many hydrogen environments. You should be able to answer with numbers, but you also should be able to look and identify the different hydrogen and carbon environments as we've done right here.